right. I have chosen a bunch of questions, stoichiometry questions, some limiting reagents, and some percent yield. All right. I am going to be putting these on JetNet as well, so that you'll hear me say these problems, but I will put them on JetNet as well so that you have them written down. Okay, the first problem says ammonia gas reacts with oxygen gas according to this equation. Okay, so make sure I don't drop my stuff. We have ammonia gas and it reacts with oxygen to give me nitric oxide, nitric monoxide to be correct, and let's see, water. Okay. As always, as I mentioned in the lecture, the first step to any stoichiometric problem is you need to balance the equation. This isn't balanced, so how do I go about it? Well, first, I see that I have 3 hydrogens here and only 2 here, so I can make this from an odd to an even by putting a 2 up front here. Okay, now let's see. If I put a 2 over here to balance that out, will that take care of it? Let's see, I have 2 times 3. I have 6 hydrogens here, but only 2 here. So if I put a 3 here to balance my hydrogens, now what do I have? I have my nitrogens balanced, and I have my hydrogens balanced, but what about my oxygens? 2 plus 3 is 5, and I only have 2. I can't really put a 2.5 here because we have to have whole numbers, which means that, give me a second here, which means that I need to multiply everything by 2. Okay, so try not to erase stuff that I don't want to erase. Okay, so if I multiply everything by 2, if I have a 4 here, 4 nitrogens, and then I had a 3, so this makes 4 times 3 is 12, and I put a 6 here, 6 times 2, that gives me 12. Now let's look at the oxygens. I have 4 oxygens plus 6, that's 10. Divided by 2, if I put a 5 here, then I have everything balanced out. All right, that's the first step. Now let's read the next question. How many moles of oxygen gas are needed to react with 23 moles of ammonia? Okay, so I'm given, this is my ammonia, I'm given 23 moles of that, and it asks me to calculate how many moles of oxygen will react with the ammonia. Once again, these coefficients are molar coefficients, so because I'm given 23 moles of ammonia, that is in the correct unit. I have moles. I can use then the molar coefficients in this chemical reaction to calculate an amount of moles of any of these other substances. But be careful, you always start with the amount that you're given. I'm given 23 moles of ammonia, And now I can use the molar ratio as a conversion factor. What do I know from this reaction, balanced reaction? I know that I need 5 moles of oxygen for every 4 moles of ammonia. I want the moles of the ammonia on the bottom because I want them to cancel out. So I put 4 moles of ammonia at the bottom, 5 moles of oxygen on the top. This, as I said, will cancel out. And if I do this calculation, I should get 29 moles, or thereabout, 29 moles of oxygen. Okay, that's A. Now let's go to the next problem. How many grams of nitrogen monoxide are produced when 25 moles of oxygen gas react with an excess ammonia? Remember, when you read excess, that means that you kind of ignore this because we know that the oxygen is going to run out faster. That's going to be my limiting reagent, so I don't need to worry about figuring out which one's going to run out faster. The excess part tells me. I am asked to figure out how many grams this time, how many grams of nitric oxide are going to be made when 25 moles of oxygen react. Okay. I have 25 moles of oxygen, so I start with that number. 25 moles of oxygen. Now, when I need to convert from moles of something to moles of another substance, I go back to the chemical reaction, the balanced chemical reaction. What do I see from this reaction? I set up my fraction here, my conversion factor, in such a way to cancel my moles of oxygen. I know from this reaction that for every 4 moles of nitrogen monoxide that is produced, I use up 5 moles of oxygen. I want the moles of oxygen on the bottom, so I will write 5 moles of oxygen are used up for every 4 moles of nitric monoxide or nitrogen monoxide that are being made. My moles will cancel, and if I do this math correctly, I get 20 moles of oxygen. But it didn't ask for how many moles, not oxygen, but nitrogen monoxide. So NO. But it did not ask for moles of NO. It asked for grams. Now that I have the amount in moles, I can use the molar mass of nitrogen monoxide, NO, to figure out how many grams of NO that is. So once again, start with the amount you're given. Do not start with a molar mass. Write 20 moles of NO multiplied by, and I am just writing the molar masses right now. I assume that you already know how to calculate the molar masses, so I'm not going to sit here and calculate every molar mass. If you don't, just review it, make sure you know it down cold. So 20 moles of NO multiplied by, I want the moles at the bottom, so 1 mole of NO weighs 30 grams. My moles will cancel, and I get 600 grams of NO. So I successfully took an amount in moles of one of my reactant and figured out an amount in grams of a product. Okay, let me erase this this part real quick so that we can move on to the next part. It's a little harder to erase these types of markers. All right, almost there. Okay, the next problem says if 24 grams of water are produced, how many moles of nitrogen monoxide are formed? Okay, so if 24 grams of water are produced, how many moles of nitrogen monoxide are produced as well? Okay, once again, I will start with the amount that I'm given. It's 24 grams of water. 24 grams of H2O. Now, once again, anytime you see an amount in grams, you want to convert that to moles because you cannot use these coefficients here as molar ratios if you have an amount in grams because they relate amounts of moles. I can convert this to a molar amount because I can figure out the molar mass of water, which is about 18 grams per mole. However, I want to write this in such a way to get rid of my grams. So if I use 18 grams per mole, I will write 18.01 grams of water for 1 mole. Okay, I know that 1 mole of water weighs 18.1 grams. So my grams will cancel, and I get 1.33 moles of water. This is how much water 24 grams is, how many moles. Okay, this is how many moles of water I made at the end of the reaction. What else do I know from this balanced equation? I know that for every 6 moles of water, I also make 4 moles of nitrogen monoxide. But I don't have 6 moles of water. I have 1.33 moles. So we can use this ratio to figure out how many moles of nitrogen monoxide I form from 1.33 moles of H2O. So if I start with 1.33 moles, 1.33 moles of H2O, and then I write my fraction in such a way to get rid of my moles of water. So I know 6 moles of water are produced for every 4 moles of nitrogen monoxide as well. My moles will cancel out, and if I do this math, I get 0.889 moles of NO. And that's what it asks me, how many moles. Now, all of these problems are a combination. You have some amounts in grams, and it asks you to just find the moles. If it had asked me to find it in grams, I would have one extra step. So I've tried to pick problems that have a combination of these. We'll have a few more so the last one where we start with grams and we have to end up with grams. But I want to show you one more way to do this, to set up this ratio, that I remember talking with one of you and it seemed easier. So I will do it that way just to see. You'll have 2 different ways, and whatever is easier for you, you can use that. What we know is that, so we have 6 moles of H2O make 4 moles, or are made, when 4 moles of NO are produced. What if I have 1.33 moles instead? How many X? Because I don't know that. So if it's easier for you to set it up this way, then set it up this way. So I form X moles of NO. I can cross multiply these and set them equal to each other. So by cross multiplying, I mean 1.33 moles multiplied by 4 is equal to 6 moles multiplied, I'll do it this way, multiplied by x. So now to isolate x, I divide both sides by 6 moles. And we're back to this calculation here. If you want to set it up this way, it's fine. If it's easier for you to set it up this way, that's fine too. I just wanted to show you this other method. I grew up doing it this way, but here in the States, this is the version that people use all the time. So I wanted to show you both, and you could pick and choose whatever's easiest for you. Let's do one more problem with this reaction, and then we'll move on. Okay, the next problem says how many grams of oxygen are needed to react with 6.7 grams of ammonia. So now we have an extra step. We start with an amount in grams and we go all the way to an amount in grams. I am going to give you a little condensed version of what we're doing that I learned when I was taking chemistry first. So here's an amount in grams, here's an amount in moles, and grams. If you're given an amount in moles, you go from grams to moles, back to grams. So we have this continuity here. And I still remember my professor saying grams to moles to grams. That's the flow. Now you don't have to have all of these amounts, all of these steps necessarily. You might start with moles up here, convert it, moles of a substance, convert it to moles of another substance, and then back to grams. Or you can start with grams of one substance, convert it to moles, then convert it to moles of another substance and stop there. But this is the longest version of it. To go from grams of one substance to moles of another, you must use the molecular weight of that substance. You cannot use anything else to go from grams to moles or moles to grams. You have to use the molecular weight of the substance. Same with here. Now these are two different substances, but you have to use the molecular weight. To go from moles of one substance to moles of another, you use the balanced chemical reaction. Okay? You cannot use the balanced chemical reaction unless you have an amount in moles. You cannot use the balanced chemical reaction if you have amounts in grams. To do that, you first have to convert to moles by using the molecular weight of whatever substance you have. Then once you have that amount in mole, you go up here to the balanced chemical reaction, convert it to moles of another substance, and then you can convert it back to grams of that same substance you converted up here to moles by using molecular weight. And we'll do this in this next problem. But I wanted to show you kind of, just so that it gets ingrained in your head that to go from grams to moles or from moles to grams, you have to use the molecular weights of the substances, but from moles to moles, you go back to the chemical reaction. So this last problem will have us do all of those steps. So we'll start in grams, and then we'll end up in grams of different substances, but they're both amounts in grams. Okay, what am I told? How many grams of oxygen are needed to react with 6.78 grams of ammonia? So I have 6.78 grams of ammonia, NH3, and I want to figure out how many grams of oxygen need to react with that many grams of NH3. First thing you need to do, once again, you cannot use these molar coefficients unless you have a molar amount. So we have to convert the grams to moles by using the molar mass of NH3 because that's my substance. And I do that by finding the molar mass of NH3, which is about 17 grams. Whoops. I will see, I put it on the wrong way. I want my grams to cancel. So I will put the grams at the bottom, 17 grams of NH3. That's how much 1 mole of NH3 weighs. My grams will cancel, and I will have 0.399 moles of NH3. That's how many 6.78 grams are. Obviously, the amount in moles is going to be smaller than the amount in grams because you divide by the molar mass. Okay, now that I have moles of NH3, I can go back to my balanced chemical equation and I can relate it to moles of anything else. But in this case, I want to relate it to moles of oxygen. So I, once again, start with this amount that you're given, 0.399 moles of NH3. Multiplied by, so I write my conversion factor in such a way to get rid of my moles of ammonia and to end up with moles of oxygen. So I know 5 moles of oxygen need to be used for every 4 moles of NH3. My moles of NH3 will cancel out, and this will give me 0.499 moles of oxygen. Okay, if you remember those steps, we had grams of NH3, we moved to moles of NH3. Here we move to moles of water. Now we have to move to grams of water, and we do that by, or not water, I'm sorry, oxygen. And we do that by using the molar mass of oxygen. So once again, we have amounts in grams that we want to convert, or one we have grams and we want to convert to moles, and one we have moles and we want to convert back to grams. We have to use the respective molar masses. So I have 0.499 moles of oxygen, and I want to convert this to grams. Never start with a molar mass. I have stressed this and will stress it till I'm blue in the face. Do not start with the molar mass because then you'll always get the wrong answer. Always start with the amount that you're given, which is what we calculated up here. This, I want to write the molar mass of oxygen in such a way to get rid of my moles and have grams on the top. I know that O2 has, so 1 mole of O2 weighs 32 grams. Moles will cancel out, and if I do this math, it gives me 15.95 grams of O2. So to react all of the amount of NH3, so 6.78 grams, which is what we started at the top, requires 15.95 grams of oxygen. Okay, so once again, we had grams, 2 moles, 2 moles, 2 grams. We started with grams of NH3. We used the molecular weight of NH3 to convert to moles of NH3. Then we used the reaction, balanced reaction to convert from moles of NH3 to moles of oxygen. Then to go to grams of oxygen, we use the molecular weight of O2, of oxygen. Okay, that is the first set of problems with this. So that's the end of the problems with this particular reaction. We'll do another set of problems with another reaction, just so we can get the stoichiometry down. This is the second set of problems with a different balanced chemical reaction. So let's read. The compound calcium carbide, which is CaC2, is made by reacting calcium carbonate with carbon at high temperatures. So before we get to CaC2, we know that we react calcium carbonate, which is, if you should know by now, CO3 is the carbonate ion, calcium is Ca, with carbon at high temperatures to form calcium carbide, CaC2, and carbon dioxide. Okay, first of all, let's make sure that I have the correct neutral compound here. CO3 has a 2- charge. Calcium has a 2+ charge, so I'm good there. Okay, and the rest of them we're not going to worry about. But at least the calcium carbonate, we want it to make sure that it's written correctly. Okay, now as I look at this, I can see that it's not a balanced chemical reaction. Okay, I see I have 3 oxygens here, but only 2 here. So what do I need to do? I need to convert my odd numbers into even. I do that by putting a 2 in front. So now I have 6 oxygens, but I only have 2 here. To make those equal, I can put a 3 in front of the CO2. Okay, now I have 2 calciums, only 1 here. So if I put a 2 in front of that calcium, that balances out. So I have 2 calciums, 2 calciums. 2 times 3, that's 6 oxygens. 3 times 2, that's 6 oxygens. Now I get to balance my carbon, and I left that last because I can put any number I want in front of this carbon. So it's much easier to balance this than it is to balance the carbon when it's in a compound like this, because if I change the carbon, I also change the other 2 elements as well. So let me count carbons on this side. I have 2 times 2, that's 4, plus 3, that's 7. What about on this side? I have 2 carbons and 1 to make it 7. All I have to do is put a 5 in front of that carbon. And now I have them. So 2 times 2 carbons, 5 carbons, 2 times 2, 4, plus 3, that's 7 and 7. That's your first step. To do any stoichiometry problems, you have to balance the chemical equations. If you don't, you will get wrong amounts every time because your coefficients are going to be wrong. Okay, let's read the next part. How many moles of carbon are required to produce 5 moles of CO2? Pretty easy. I don't have an amount in grams here. All I have an amount in moles, and I want to convert it to another amount in moles, which is the easiest step out of that grams to moles to moles to grams. I have moles, I'm converted to moles of something else, so it's just a one-step problem. Okay, I am given 5 moles of carbon dioxide, and I'm asked to figure out how many moles of carbon would be required to react. So once again, don't start with the molar coefficients. Start with the amount you're given. 5 moles of CO2 will react, and here's my coefficients. I know 3 moles of CO2 are made for every 5 moles of carbon that are reacted. I want the moles of CO2 at the bottom, so they cancel out. So 3 moles of CO2 are formed for every 5 moles of carbon. My moles of CO2 will cancel out, and if I do this math, I'll get 8.3 moles of CO2. One step, once again, I had moles, oops, not of CO2, just of C. I just noticed that I wrote the same. Okay, so I have moles of CO2 and I wanted moles of carbon. One step. I'm good with this problem. The next question, how many grams of calcium carbide are produced when 4 moles of carbon react with an excess of calcium carbonate? So now I have moles of carbon, and I'm being asked to calculate how many grams of calcium carbide are made from 4 moles of carbon. So once again, start with the amount that you're given. I have 4 moles of carbon, and I write my molar ratios in such a way that my moles of carbon will cancel out. I know that for every 5 moles of carbon, I make 2 moles of calcium carbide. So 5 moles of calcium, or of carbon, go at the bottom, and 2 moles of calcium carbide at the top. My moles of calcium cancel, and if I do this calculation, I get 1.6 moles of calcium carbide. But it doesn't ask for an amount in moles, it asks me for an amount in grams. So I need now to convert these moles into grams, and I do that by using the molar mass of calcium carbide, which is 64. So I need to get rid of my moles, so I write 1 mole of calcium carbide weighs 64 grams. My moles will cancel out, and it gives me 102 grams of calcium carbide. I hope you can see that. 102 grams. Okay, so I started for this, I added one more step. I started with moles, I used my equation up here to convert to moles of a different substance, then used the molar mass of that substance to convert it to grams. Now we're adding one more step. Well, maybe. How many moles of carbon dioxide are produced when 55 grams of calcium carbonate react with an excess of carbon? Not quite yet, all 4 steps, but now we start with grams instead of moles, and we end up with moles. So we are asked how many moles of carbon dioxide, CO2, are produced when 55 grams of calcium carbonate react. So I'm given 55 grams of calcium carbonate. And I need to find how many moles of CO2 that will make. I cannot use the molar ratios yet because I have an amount in grams. I have to convert this first to moles. I use the molar mass of calcium carbonate, which is 100 grams. So I write that in a way, 1 mole of calcium carbonate weighs 100 grams. My grams will cancel out, leaving me moles at the top, and that gives me 0.55 moles. 5 moles of calcium carbonate. Now that I have moles of calcium carbonate, I can go up here and look at my molar ratio. For every 2 moles of calcium carbonate, I get 3 moles of CO2. So now I start with the amount I'm given, 0.55 moles of calcium carbonate. I write the molar ratio in such a way to get rid of my calcium carbonate. 2 moles of calcium carbonate for every 3 moles of CO2. This will cancel, leaving me with moles of CO2. And that gives me 0.825 moles of CO2. And that's what I was asked to do. I started with an amount in grams, and I was asked to calculate how many moles of a different substance I could produce from that much calcium carbonate. Anytime you see an amount of grams, you cannot, when you start anyway, you cannot use this reaction in an amount in grams. You have to convert that first to moles. If you are given an amount in moles, you can use it because it's already in moles. But if it's in grams, then you can't do that. You have to convert it first to grams. Okay, and then let's look at another problem where we go from an amount in grams to calculating another amount in grams. So we use all three steps. These are very systematic. Once again, you just have to practice a bunch and remember the grams to moles to moles to grams. The little diagram that I showed you earlier, that will help you. Okay, then the last problem, well, no, it's the next to last. It says, so the next problem says, how many grams of carbon are needed to react with 453 grams of calcium carbonate? So I'm given 453 grams of calcium carbonate. And I'm asked to figure out how many grams of carbon will react with that much calcium carbonate. I cannot use the molar coefficients the way it is now because it's an amount in grams. Remember, grams, 2 moles, 2 moles, 2 grams. I'm right here. I'm given an amount in grams. I need to convert it in moles of calcium carbonate, then use the equation to convert it to moles of carbon, then use the atomic mass of carbon to convert it to grams of carbon. So I have 453 grams of calcium carbonate. The molar mass of calcium carbonate is 100. And I have to write this: 1 mole of calcium carbonate weighs 100 grams. This will cancel, and it gives me 4.53 moles of calcium carbonate. Okay, now that I have an amount in moles, I can use the balanced chemical reaction to go from moles of calcium carbonate to moles of carbon. I know 4.53 moles of calcium carbonate. I can use that molar ratio in such a way to get rid of moles of calcium carbonate. 5 moles of carbon. I use up 5 moles of carbon for every 2 moles of calcium carbonate. These will cancel out, and if I do the math, it gives me 11.325 moles of carbon. But I was asked to figure out an amount in grams, so I have to take, I'm right here, I started out here, grams of calcium carbonate. I converted that to moles by using the molecular weight. Then I went up here, converted moles of calcium carbonate to moles of carbon. And now I have to use the atomic mass of carbon to convert it to grams. So 11.325 moles of carbon multiplied by 12.01 grams of carbon, which make 1 mole of carbon. Moles will cancel out, and I will get 136 grams of carbon. So this is what I need. I started out with 453 grams. I need 136 grams of carbon to react with that much calcium carbonate. Okay, we got one more problem like this, and then we'll move on to limiting reagents and percent yields. Okay, then the last problem says how many grams of calcium carbonate are needed to form 598 grams of calcium carbide. So I formed 598 grams of calcium carbide. How many grams of calcium carbonate do I need? Once again, I start here. I have grams of a substance. I need to get to grams of another. Grams to mole to mole to grams. 598, that's what I start with, 598 grams of calcium carbide. I use the molar mass of calcium carbide in such a way to get rid of my grams. Molar mass is 64, so I know 1 mole of calcium carbide weighs 64 grams. This will cancel out. And it gives me 9.34 moles of calcium carbide. Okay, now that I have moles of calcium carbide, I can go up here to the balanced chemical equation and relate it to moles of calcium carbonate. Once again, start with this, 9.34 moles of calcium carbide multiplied by, okay, I know that for every 2 moles of this, I use 2 moles of that. So it's a 1-to-1 ratio, but we'll do it anyway. 2 moles of calcium carbonate for every 2 moles of calcium carbide. Now, 2-to-2 ratio is the same as a 1-to-1 ratio, but my moles of calcium carbide will cancel out. It's just good practice for you to get used to these types of problems, to write it out even if it is a 1-to-1 ratio. That gives me 9.34 moles of calcium carbide, or calcium carbonate, sorry. Okay. Now that I have moles of calcium carbonate, I can convert it to grams of calcium carbonate by using its molar mass. So I'm right here. I have moles of calcium carbonate. I need to convert it to grams. And I use the molar mass of calcium carbonate, which is 100 grams per mole. Once again, start with the amount you're given, 9.34 moles of calcium carbonate. And now I need to get rid of my moles, so I need to put moles at the bottom. 1 mole of calcium carbonate weighs 100 grams. Moles will cancel out, giving me 934, pretty easy, I don't know why I even looked at my notes, 934.4 grams of calcium carbonate. And that is how you work these types of problems. So this is the longest one with the most steps. You have 3 steps where you start with an amount in grams. You have to convert to moles by using the molar mass. Then you use the balanced chemical equation to relate it to another substance, but always an amount in moles. And then to convert that back to grams, you use the molar mass of that particular substance. Okay, if you have any questions on these types of problems, please don't hesitate to ask me. Email me and I will get back with you. Thank you. Okay, we are moving on to the limiting reagents and percent yield type of problems. Let's do these next 2 problems are limiting reagent ones, but they also have percent yields. Typically, you will see them together. So let's get started. It says when copper 2 chloride, okay, copper 2 chloride, let's decipher this. We know copper and we know chloride, okay? The charge, copper 2 tells me the charge on the copper. So copper is a 2+, but what about the chlorine? We know that that's a -1 ion, so to balance these 2, I need a 2 by the chlorine. So copper 2 chloride reacts with sodium nitrate. Learn those polyatomic ions. Sodium and nitrate is NO3. Sodium has a +1 charge, NO3 has a -1 charge, so that's already neutral. I don't need to do anything to that. And it forms copper 2 nitrate and sodium chloride. So it's a double displacement reaction. Copper 2 nitrate. Now remember, because nitrate is a -1, copper is a 2+, I need 2 nitrates. So I need a 2 down by the subscript at the bottom. And sodium chloride, NaCl. Sodium is a +1, chlorine is a -1. I don't need to do anything there. Now I need to make sure that it is a balanced reaction. I have 2 chlorines here, but only 1 here. I have 2 nitrates here, but only 1 here. So I can put a 2 up front here. That makes 2 chlorines on each side. But I change the number of sodium, so I have 2 sodiums here, 1 here. If I put a 2 up front here, that takes care, balances out my nitrates as well. So 2 sodiums, 2 sodiums, 2 nitrates. I like to think of them as a group. And I also have 2 nitrates here, 2 nitrates there, so I'm balanced. Okay, that's the first step. You always have to make sure that your reactions are balanced. Now let's continue. If 15 grams of copper 2 chloride react with 20 grams of sodium nitrate, how much sodium chloride can be formed? Notice that when you have these types of problems with limiting reagents, you will be given both amounts in grams or moles, but typically in grams of each reactant. When you are given amounts in grams for each reactant, you know that it's a limiting reagent type of problem. One of them will run out first. So let's do the obvious. The first step after we balance is to convert any amounts that we are given in grams to convert them to moles. So I'm given 15 grams of copper, so 15 grams of this, and 20 grams of this. So the first thing is to convert those to moles. I take 15 grams of copper 2 chloride, and I know 1 mole of copper 2 chloride weighs 134.45 grams. My grams will cancel, and this will give me 0.112 moles of copper 2 chloride. Okay, I converted it to moles. Now I need to do the same with sodium nitrate. So I have 20 grams of sodium nitrate, And I know 1 mole of sodium nitrate weighs 84.995 grams. My grams will cancel, leaving with moles, and that is 0.235 moles of sodium nitrate. Okay. Once again, if you just look at this, it doesn't always mean that, oh, this is the smallest amount, it will run out faster. You have to look at the molar ratios up here. But the next step is to figure out how much product each of these is going to make. The one that makes the least amount of product is going to be your limiting reagent. So if I take 0.112 moles of copper chloride, how much sodium chloride is that going to make? 0.112 moles of copper 2 chloride. What's my molar ratio? 2 moles of NaCl for 1 mole, so 2 moles of NaCl for every 1 mole of copper 2 chloride. This will cancel, and this will just multiply by 2, gives me 0.223 moles of NaCl. Okay, so if all of those 15 grams of copper 2 chloride reacted, it would give me 0.223 moles of NaCl. How many moles of NaCl would I get if I reacted all of that 20 grams of sodium nitrate, or 0.235 moles? So I can take the amount of moles, 0.235 moles of sodium nitrate, and now relate it to NaCl. It's a 2-to-2 ratio, or a 1-to-1 ratio, so 2 moles of NaCl for every 2 moles of sodium nitrate. So I get I should get 0.235 moles of sodium chloride. Okay, this is the smallest amount of product, so this is gonna, this is how much I make. My copper 2 chloride is gonna run out faster because it gives me the least amount of product. So that is going to be my limiting reagent. Which one? The next question says, which one is your limiting reagent? Copper 2 chloride is the limiting reagent. Okay. Now, how many grams of copper 2 nitrate is formed from this reaction? Well, I know that this is going to be the limiting reagent, so that is going to determine how much product is going to be made. So I am going to erase the rest to give me some space here. So bear with me. Once again, I can take that amount of moles of copper 2 chloride and relate it to the copper 2 nitrate that I have up here. So 0.112 moles of copper 2 chloride, I can relate it. It's a 1-to-1 ratio. 1 mole of copper 2 nitrate for every 1 mole of copper 2 chloride. This is canceled, so it would make 0.112 moles of copper 2 nitrate. Now, if 11.3 grams of sodium chloride are formed in this reaction, what is the percent yield? Okay, I had it earlier, so we solved this, and I'm going to erase it, and I'm going to write back, you can look at your notes, the amount in moles of sodium chloride that we figured out earlier, and I just erased it because I needed room. So if all this 0.112 moles of copper 2 chloride react, it would give me, or it would make, where is it? 0.223. We said it would make 0.223 moles of NaCl. Now I need to find how many grams of NaCl that is. So I start with 223 moles of NaCl. To convert this to grams, I use the molar mass. 1 mole of NaCl weighs 58.44 grams. My moles cancel, and this gives me 13.03 grams of NaCl. Now, remember, anything we calculate is the theoretical yield. Anything that the problem gives us, it's the experimental yield. The next question then says if 11.3 grams of sodium chloride are formed in this reaction, what is the percent yield? So the problem says that I have I have 11.3 grams of NaCl that were formed. What is my percent yield? I calculated that I should get, if I collected everything, I should be getting 13.03 grams. But because of the second law of thermodynamics, I get less than that. So I need to figure out the percent yield. Now remember, percent yield is given as the actual, or the experimental part, what you collect, so the actual 11.3 grams, divided by the theoretical, what we calculate from the balanced chemical reaction, 13.03 grams, multiplied by 100. My grams obviously cancel out. This will give me 86.7%. Now notice, if I had flipped these two, I would have gotten a number over 100% yield. You know you've done that wrong because we don't get 100% yields. We get much less. And so if that's the case, then flip them over. But just double check, be mindful of that this number should never be over 100 unless you have impurities or you messed up your experiment. So then go back and check your math. Okay, this is the first problem with limiting reagent. Let's look at one more. Okay, problem number 2 for limiting reagents. When lead-2 nitrate, so lead-2 tells me the charge of lead. Lead-2 nitrate is NO3, and it's a minus. So to make this neutral, I need 2 nitrates. When it reacts with sodium iodide, sodium is a +1, iodide is a -1, so we're good there. It produces, once again, it's a double displacement reaction. It produces lead to iodide, 2 plus, -1. I need 2 of these. And the sodium nitrate. These are a +1 and a -1, so I don't need to make these, it's already neutral. But it's not balanced, okay? The compounds are neutral, but the whole equation is not balanced. I have 2 nitrates here, only 1 here. I have 2 iodides, 1 iodide. So if I put a 2 up front here to balance my iodides, I have 2 sodiums, 2 sodiums, 2 nitrates, 2 nitrates. Now I'm balanced. Okay. If I start with 25 grams of lead-2 nitrate and 15 grams of sodium iodide, how many grams of sodium nitrate can be formed? Once again, you're given amounts for both reactants. That means that it's a limiting reagent problem. One of these is going to is going to run out faster. So you have to figure out which one is going to run out faster, and you do that. You first convert amounts from grams into moles. You relate that to the product. Whatever gives you the least amount of product, that is going to run out faster. It's going to be the limiting reagent. So I have 25 grams of this, and I have 15 grams of this. First step, I convert those to moles. So 25 grams of lead 2 nitrate. Convert that by the molar mass. I know 1 mole of lead 2 nitrate weighs 331.2 grams. My grams will cancel out. This gives me 0.0755 moles. Okay. Convert now 15 grams of sodium iodide, and I do it the same way by using the molar mass of sodium iodide. 1 mole of sodium iodide weighs 149.89 grams. My grams will cancel and will give me 0.100 moles. Okay, now I'm not sure which one is going to run out faster. Don't make that prediction. You need to relate it to how much product it's going to make. So if I see this many moles of lead 2 nitrate, to convert it to moles of sodium nitrate, I use the molar coefficient. So I have 2 moles of sodium nitrate for every 1 mole of lead 2 nitrate. This will cancel out, and I'm running out of space here, but it will give me 0.151 mole of sodium nitrate. How about the sodium iodide? It's a 2:2 or 1:1 ratio. You can do that 2 divided by 2, but this is the same. It will give me 0.100 moles of sodium nitrate as well, because it's a 1:1 ratio. Okay, this is going to run out faster. That's what I said. By looking at just these 2 amounts, you would have said, oh, this is going to run out faster. But no, you have to take into account the molar ratios. This is going to give me the least amount of sodium nitrate. So sodium iodide is my limiting reagent. Okay, now, if 6 grams of sodium nitrate are formed in the reaction, what is the percent yield of this reaction? Okay, well, the first thing is take this amount of sodium nitrate and convert it to moles by using the molar mass of sodium nitrate. 0.01 moles of sodium nitrate multiplied by its molar mass. So 1 mole of sodium nitrate weighs 84.995 grams. Moles will cancel, and this will give me 8, and I'll just round, 8.5 grams of sodium nitrate. This is my theoretical yield. This is how much I should be getting if I get 100% yield, but I don't. It tells me that I only collected 6 grams of sodium nitrate, so I need to calculate the percent yield. Percent yield is actual over theoretical times 100. My actual, it tells me, is 6 grams. Theoretical is what I calculated, 8.5 grams times 100. And if you do that math, it should give you 70.6%. That's my yield right there. Okay, I've got one more problem that looks at the percent yield in the opposite direction, just to give you another type of problem to think about. So I'll erase this and we'll be back to one more problem. Okay, we're back to the last problem, and we'll use the same equation for this problem. If the percent yield for lead 2 iodide was 72%, so I'm told the percent yield is actually 72%, and the actual amount that was collected of lead 2 iodide is 12.5 grams. What is the theoretical yield from this reaction? Okay, now we're kind of going backwards. We're given the actual amount that was collected, we're given the percent yield, we have to find the theoretical yield. Well, what do I know? I know that the percent yield is equal to the actual amount over theoretical times 100. And this, the problem tells me, is equal to 72%. Okay? My actual I know. I don't know the theoretical, so I can say my actual is 12.5 grams divided by x grams is equal to, if I divide both of these sides, both by 100 to get rid of that percent, is equal to 0.72. Okay? My grams will cancel out, so my x will be equal to 12.5 divided by 0.72, which gives me 17.36 grams of lead 2 iodide. That was my theoretical yield. Okay? Now, it says, what theoretical amount of sodium iodide would have been needed to produce this much amount of lead iodide? So this is the theoretical, this is what I should have gotten. How much sodium iodide would need to be used up to produce this amount? Okay, once again, we have an amount in grams, we have to convert it to moles before we use the balanced reaction. So I have this many grams of lead 2 iodide. To convert that to moles, I know 1 mole, or I can figure it out, 1 mole of lead 2 iodide will weigh 461.01 grams. My grams will cancel, and this gives me 0.038 moles of lead 2 iodide. Okay, now that I have an amount in moles of lead 2 iodide, I can relate that to an amount of moles of sodium iodide by using that reaction. So I start with what I'm given, 0.038 moles of lead 2 iodide, multiply by I write the mole ratios in such a way, so 1 mole of lead 2 iodide is produced for every 2 moles of sodium iodide that is used up. This cancels out, and I should get 0.0753 moles of sodium iodide. Now that I have the moles of sodium iodide, I can convert it to grams by using sodium iodide's molar mass. So I start with 0.0753 moles of sodium iodide multiplied by, okay, I know 1 mole of sodium iodide weighs 149.98 grams of sodium iodide. This cancels out, and it gives me 11.29 grams of sodium iodide. So let's recap. If all of this amount of lead, my theoretical amount of lead to iodide, to produce that much of lead to iodide, I would need to use up, theoretically speaking, 11.29 grams of sodium iodide. But even if I had all this amount and I used it, this is what it would have given me. But in fact, it only gave me 12.5 grams because my percent yield was only 72. Okay? These are the types of problems that involve percent yield and limiting reagents and stoichiometry altogether. They can be a little confusing at first, but the more you work, the more problems you work, the easier it's going to get. I will have these problems in PDF form on JetNet, so you can actually look at the problem, read it, as well as look at the solution that I have here, the video. If you have any questions, please send me emails, and we'll go from there. So, thank you.